Hi, I got cut off in that last video and I just reloaded PDF Annotator again. Um, where we were is just defining the moment generating function. Get that pen. And we were saying that comes out to be this infinite sum of, notice that there's moments in each of these. Writing it this way, you can see like there's the first moment, there's the second moment, there's the kth moment. So nicely, if I do things with derivatives, I can isolate these moments. There's a nice rule. If you take the kth derivative of the moment generating function and evaluate it at t equals 0, you get the kth moment. I think it's easy to show that. So for example, to get the first moment, I take the first derivative. So look at this expression, and let's take the first derivative. This first guy is 0. And then I'm taking the first derivative with respect to t. I should have said that. Yeah, that was not very clear. First derivative here with respect to t is just expected value of x. And then the first derivative here would be 2t over t. So this is t, expected value of x squared. Plus the next guy, when I'm going to get this, would have been t cubed. So this would be 3t squared over 3 factorial, expected value of x cubed, plus I keep going. So notice now, if I put in t equals 0, it's going to wipe out every term after this first term. So if I take the first derivative, stick in t equals 0, all these disappear and I'm left with the expected value of x. Same way, if I take the second derivative, right, this is still 0. Expected value of x is a constant, so this is 0. Take second derivative of this, there's a t in front of that now, right? So we get expected value of x squared. Now this is going to be, I don't have a place to write this, but the derivative here would be 3 times 2 times t to the first over 3 factorial, expected value of x cubed. And notice that this all cancels out, so I just have a t in front of there, and then so forth and so on. And when I put in 0, all the terms past x squared wipe out, and I just have expected value of x squared at the second derivative. So that's what I'm trying to show right here. Just, I mean, imagine you have this long thing, just keep taking derivatives, and well, that's exactly it. Take the derivative t equals 0, we get this guy. Take second derivative, we'll get this guy. Take kth derivative, we'll get this guy. So let me show you in one problem. Y is exponential. Determine its moment generating function. So my of t should be the expected value of e to the yt, right? That's just definition. This is just definition of expected value. Y is continuous, so this is just the integral of, here is f of y times e to the yt dy, and y's go from 0 to infinity. So this is just, if you don't mind, I think I'll pull lambda out front. This is e to the, let's say, y to the t minus lambda, right? Because when I multiply, I add exponents, so I'm pulling out the y, and that leaves with t minus lambda dy. Let's take a antiderivative. So this is e to the y t minus lambda all divided by t minus lambda, right? And this goes from y equals 0 to y equals infinity. Sorry, I'm being a little bit loose here, right? I mean, I should take a limit at y equals infinity, so I'll just put little quotation marks up here and hope that you don't mind that I'm saying something a little bad, because t is less than lambda. When y goes to infinity, t minus lambda, this is a negative value. So this is all going to go to 0. And then when I plug in, or I should say minus, when I plug in 0, I'm going to get lambda e to the 0 divided by t minus lambda. So this should be a negative lambda over t minus lambda. Or you could rewrite it as lambda minus t. That's the moment generating function. So if I come down here, what I did is I decided to go ahead and put this in Maple. And I wrote a whole Maple worksheet. Let me bring up that. You can see it right here. So I made some assumptions. In Maple, it's easy to do that. You just say, assume this. Okay, so it's just showing what f is, and then I found its here's its moment generating function, right? This is what we just did. The first moment, take the derivative. That's all I'm doing right here. Take the derivative at t, and then stick in t equals 0, and you'll get the first moment, which is the mean. So let's put it there and execute it. So the first moment of an exponential is 1 over lambda, which is the mean of an exponential. I can find the second moment. Remember, that's not the variance, that's just the second moment. And then the variance is the second moment minus the first moment squared, and this is what you get. So, oh, I guess right here all I'm just showing you is we could take the 10th moment. Looks like I'm going to crash that, so let's just put cancel and go back to that. So all I did right here, let's move this out of the way. You can see I found the first moment. I'm just showing the Maple Code second moment. And then I went ahead and posted all of this. This is all an Angel. I posted a Maple worksheet for every example how I did it with Maple. So if you'd like to do this in Maple or take derivatives by hand, however you want to do it, I have a Maple worksheet for that. So I'll do a few more examples. I'll open another video, do a few more, and then probably move on to 11.2. Hi, we started another new section this week, Chapter 11, which it probably seems kind of strange because we were doing all this stuff with distributions and joint distributions, and now Chapter 11 concentrates on something that we call moment generating functions, and I usually just shorthand MGF. And the reason why we do moment generating functions, well, first it can give us moments of a random variable, but it can also, I think it's much more important for other things. Namely, it gives us a nice way of learning how to sum independent random variables. Otherwise, this can be very, very difficult to add random variables like x plus y or any combination. This is a very, very, very tough problem in probability, so that's one reason why we use moment generating functions, because they're very helpful for this, to find out the distribution of sums. Alone, I mean, it's nice to see what moments, how to determine moments. There's a very nice way to do that, but in general, this is the more important reason for doing them. So we have a comic, and so I thought I would just introduce them in the first video and then do some examples in the next one. So when we talk about moments of a random variable, that's just the expected value of x raised to the kth power, where k is the moment I'm trying to determine. So the first moment is just the expected value of x to the 1, which you already know is the definition of the mean mu. The second moment is expected value of x squared. That's why I say second moment. This isn't the variance, but we know that the variance is the combination of, here's the second moment minus the first moment squared. The kth moment is just expected value of x to the k. And there's other things we can find with moments, like skewness. Skewness is like the amount of the distribution in a tail. Like we'd say this guy is right skewed because it has a long right tail. So expected moments of higher powers like x cubed, x to the fourth. You can find things doing combinations like skewness, kurtosis. Kurtosis is just the peakedness, like how peaked, flat across or tight a distribution is. A nice property of moment generating functions is we can distinguish random variables by their moment generating functions, because no two different random variables have the same MGF. So if you can identify a random variable's moment generating function, then you know what distribution it has. So this is a very nice property. What is the definition? So we should get to the definition now. Right now, all I'm just saying is moment generating functions are expected value of x to the k. So how do we find, or what's the definition of a moment generating function? Here it is. The moment generating function of random variable x in terms of t is expected value of e to the tx. And we know how to find expected value of a function of a random variable. We just use law of unconscious statistician. So down here, that's all I'm doing. This is expected value of e to the tx, so I put e to the tx times p of x times x, so it's just e to the tx times p of x. This is just that law, right? Remember, expected value of something like x squared was just the sum of f of x times x squared. So I'm just using this as my inner function right there to put p of x times expected value 2x. So if x is continuous, same deal. Notice the only difference, if it's discrete, we have the nice sum, and continuous, we have a nice integral. And sometimes, of course, this integration might not exist, so you might not have a moment generating function for some random variables. Same way with the discrete. So let's go down and notice now why the moment generating function finds means and variances for us. This is, I think, really cool. So I'm going to assume x is a continuous random variable. So the definition of the moment generating function is just this. So all I'm doing right now is the definition. And now I'm going to write out the power series. Oh yeah, these things come back to you from calculus. The power series of e to the tx is just this, so I'm just substituting this in for e to the tx. Oh, I hope this doesn't stop or I'll be sad. Remember this happened to us before. Let me see, maybe I can switch to another program and come back. No. Well, you probably can't see this, but so all I've done right here is definition, and then I'm going to go ahead. You can see the next line, so let's just go there. If I multiply 1 times f of x, I get this. If I multiply t of x times f of x, I get this. So I'm just going to expand and then separate them into separate integrals. You can see what I'm doing there, right? This is going to be an infinite sum of these integrals. Well, 1 times f of x dx over this interval is just 1, because this is the definition of a valid probability density function. This right here, x times f of x, is just expected value of x. X squared times f of x is expected value of x squared. X cubed would be expected value of x cubed. Down here, this is expected value of x to the k. So notice nicely, the moment generating function can be written this way as an infinite sum. We're going to use this then to find means, variances, etc. So I think I'm going to stop and see if I can start a new annotator video. I don't want to lose what I already have, so